Hey guys, welcome back to another video, and today we're going to be solving the LeetCode question, maximum XOR of two numbers in an array. Alright, so we're going to be given a non-empty array of numbers, and we want to find the maximum result of the XOR between any two numbers. So whatever the maximum value is, we want to find that. So in this case, we're given this array, and the output is actually 28. And we get that by finding the XOR between 5 and 25. And that ends up giving us 28. So we're finding out when we take two numbers, find the XOR of them, what is going to give us the maximum value. Alright, so how can we actually find this out? So in order to do that, what we're going to do is, let's just start off from the beginning. So what I'm going to do is, I'm just going to write a quick for loop. So for x in nums, and let's just print out how these numbers look in their binary form. Alright, so binary x. Okay, and let's print this out over here. Alright, so this is the standard output that we end up getting, and let's just copy this. And what does this actually mean? So if you don't know what that means, it's just the binary representation of the number. And for example, 1 and 1, that represents the value 3. And one thing you want to realize is that all of these have different sizes. So what we want to do is we want to rake it in such a way that they all have the same size. So how can we do that? So over here, I have a binary to decimal number converter. So I'm going to write 1, 1. And when you convert that, you're going to get the decimal value 3. But one thing you really want to notice is, let's say if I add a ton of zeros on the left-hand side. And so I just added a ton of zeros, and now let's convert it. And the value still stays the same. So we're going to use that property in order to make everything over here the same length. So normally, just for this question, let's make it simple. And which one has the maximum length? So the one which has the maximum length is whatever that value is. And we want to make everything the same length as that. So in this case, the length of 5. So we're just going to remove this. So we have 1, 1, 0, 0, 1. So that's the maximum length. So we want to make everything that length. So let's just do that real quick. Alright, so this is what we actually end up with. And now everything has the same length of 5. And they all still represent the same values. So now what I'm going to do is, so now let's try to see how we can actually put this in some sort of data structure in order to get out whatever the maximum XOR is. Okay, so first thing what we're going to do is let's try to understand what XOR actually is. So what is XOR mean? So it's a binary operation. So let's say we have 0, 0, 1, and 1. And then we have 0, 1, 0, 1. So both of those represent a binary number, right? And what we're going to end up doing is we're going to perform the XOR operation. And in Python, it's represented using that. So whenever we have any two same values, so if we have 1 and 1 or 0 and 0, then in that case, where the output of the XOR operation is always going to be 0. So in this case, we have 0 and 0, so this is going to be 0. And we have 1 and 1, and this is going to be 0. And the other case is when both of them are not the same. So we have 1, 1, and we have 1, 0. So two different numbers. So over here, we have 1 and 0. So in that case, we're going to output a value of 1. So then over here, we have 1, and we have 0 and 1. And in that case, they're still both different numbers. So we're also going to have an output of 1. So over here, we're going to get an output when you find the XOR between these two. It's going to be 0, 1, 1, 0. All right, so now that we have this, what we want to do is how can we actually use this information and find the XOR? So there's two things that we can do. We can find the XOR of each element against each element, right? But the thing is, this question wants us to find it in big O of n runtime. So to do that, we're actually going to end up using a tree-based data structure called a trie. And how you do this is pretty interesting, so let's just go by it step by step. And if you don't know what a trie is, it should be really clear by the end of this. Alright, so every trie starts off with a root node. So this root node does not hold any value. Just think of it as a master node which just holds everything under it. Okay, so what is actually going to go under this? Well, all that's going to go under that is going to be each of these values. So we're going to stick with the same example as in the question. And we're going to add these values bit by bit to our node over here, to our tree over there, sorry. So let's add this. So we have 3 zeros and 1, 1. So over here, we're going to have 0, then 0, then 0 again. So 3 zeros, and then 1, and then we have 1 again. Okay, so over here, we represented the first number. So we have 0, 0, 0, 1, 1. So that is one of the numbers. Cool. So now we can go on to the next number, which is 0, 1, 0, 1, 0. Okay, so how would you normally do this? So normally you would be like, okay, so I can just do 0, then 1, and so on and so forth. But when it comes to a trie-based data structure, what we do in a try is we make use of the existing data structures or nodes, right? So in this case, the first element is 0. So we're going to check from our root whether 0 exists. And if 0 does exist, we're going to use that 0 for our other number. So in this case, we're just going to reuse the 0 over here. So over here we have 0, and then we have 1, 0, 1, 0. And over here, 1 does not exist. So then we're going to create a new node with the value 1. So 0, 1, okay, 0, 1, then 0, 1, 0. So again, 0, then 1, and then 0. Okay, so we have this over here. And now let's keep doing it for all of our elements. So over here, we have 0, 0. So we already have both of them covered. And then we have 1, 0, 1. So 1 comes over here, then 0, and then 1. Okay, sorry if it's a little bit clumsy. I know it's a little bit clumsy, but yeah. Okay, now over here we have 1, 1, 0, 0, 1. So how do we actually take care of that? So in that case, we're going to create a new node since we don't have anything representing 1. So that's going to start off over here with 1, and then we have 1, 0, 0, 1. Okay, so 1, then 0, then 0, and then 1 again. Okay, so now we represented that, and we have finally a few more. So 0, 0, 1, 0. Okay, 0, 0, 1. So we have 0, 0, then 1 over here, and the 0 is just going to be a 0 over there. Okay, perfect. And then 0, 1, 0, 0. Okay, 0 and 1, we have that. Then we have 1, 0, and we need 2 more zeros. So we're going to have 1 over here, 1 over here. Okay, sorry, that's super clumsy, but hopefully you get the idea behind it. Okay, but now the question is, how can we actually use this to our advantage? So how can we actually find the maximum XOR using this? So the answer is going to be pretty interesting, right? So what we're going to do is we're going to go by this level by level per se. So our first step is when we looked at our XOR function, how do we get the highest value? Okay, so you get the highest value when we have two bits which are not the same. So what does that mean? So when we have 0 and 1 or 1 and 0, when you perform the XOR operation on either of these, you're going to end up with a value of 1. And when you have a value of 1, you are going to get a higher value, right? The number is going to be bigger than when we had a value of 0. And the condition which is going to give us a lower value is when we have two of the same thing. So if you have 0 and 0 or 1 and 1, we're going to get when we perform the XOR operation, we're going to get a value of 0. And well, 0 is not going to give us a number as big as when we use 1. Okay, so now that we have that, how can we actually use this try in order to get the value? So what we're going to do is we're going to iterate through the bits of each of our numbers. So over here we have our first number, right? So the first number follows this path. So let's iterate through it, and we have 0, okay? So what are we actually looking for? So over here, what we're looking for is we're trying to look for however we can optimize, find the maximum value possible when perform the XOR operation. And how can we get the maximum value? And the answer to that is when we have a value of 1. So now what we're going to do is we're going to look for a value of 1. So we're currently at our root, and we went over here, and now we're looking for a value of 1. So over here, we're going to check if 1 exists. Does 1 exist? And the answer is true. So 1 does exist, which is right over here. And what that means is that we're going to use that as our second number. So this is going to be the other number per se. So think of it as two numbers. Okay, so now let's go down after this. So we're following this path over here for the first number. So now we have 0 again. And when you have 0, what are you looking for? You're looking for 1. So now you go to this number's child and check if it has a 1. Does it have a 1? It does. So now we end up going to that. Perfect. Now again, we go to 0 over here. And again, to find the maximum value, what are we looking for? We're looking for a 1. But is there a 1 over here? So is there a 1 like that? There is not a 1. So when there is not a 1, we need to compromise and just go with the 0. And why 0? Because, well, there's only two options, 0 or 1. So there's no 1, so that means we have to go with the 0. So we end up with the 0 over here. Then over here, what do we end up with? We end up with 1. And the best option would be 0. So we have 0 over here. And then we have 0. And the best option is 1, which is, again, perfect. So now what is the answer for this going to be? And the answer for this is going to be the XOR operation between them two. So we have 0, 0, 0, 1, 0. And then we have 1, 1, 0, 0, 1. Perfect. So perform the XOR operation. We get 1, 1, 0, 1, 1. Okay, so this is one of the values you get. And we're kind of just going to hold this. So just for the sake of this explanation, we're going to have this value sitting outside. And now what we're going to do is we're going to repeat this for all of our numbers. So we're done with that. And now what we're going to do is we're going to go on to the next number over here. So now we're done with this over here. So we might end up trying this over here, right? So that's another number. So let's just do the same step. So 0. So when you have 0, you want to look for the 1. We found 1. So I'll just write that simultaneously, 0, 1. Then we have 1 over here, but there is no 0. So we have to end up with whatever we have. So in this case, that's 1, so on and so forth. And we're going to keep adding those values over here. So we can get our final or the answer that we're looking for by iterating through all of these numbers. So at one point, I'll just show it to you directly right now. What is going to be the largest number? And the answer to that is when we use this number here and this number here and perform the XOR operation with those two. So we have 0, 0, what is this over here? So 0, 0, 1, then 0, and then 1 again. Okay, so that's what we have. And on this side, we have 1, 1, 0, 0, 1. So what does that end up giving us? So this is 0 over here. Then this over here is 0 again. Then we have 3 1s. So triple 1, 0. So that's what we end up with. And we're going to have that over here. And what is this number actually equal to? So before I get to that, so each time we're going to take this binary value over here, convert it to an integer. So triple 1, 0. So let's just do that. Triple 1, double 0, sorry. 3 1s, 2 zeros, convert, and that gives us 28. So that is actually our largest answer. But we don't know that yet, so we're going to end up going through all of these tri-value numbers over here. So we go through all of the numbers, and each time we find a value bigger than the one before, we're going to substitute the current value with whatever new biggest or maximum value we found. And in this case, that ends up being 28. There's nothing bigger than 28, and so we just end up at the very ending of it, returning whatever value we have. So this is how it's going to work, and the code for it is a little bit long, but it's pretty simple to understand. Right, so let's start off with the code part of this. And what I want to do first is I want to kind of make a quick template of what we're actually going to have in our code. So after we actually start coding it, we can go through it pretty fast. All right, so the first thing we're going to have is we're going to create a class for our try node. Okay, so first we're going to create a constructor for it. So underscore init. We're going to give it self. Okay, so over here, what do we want to give it? So we want to hold this try node's children. So in order to do that, we're going to be using a dictionary to do that. So I'm just going to be using Python's inbuilt dictionary, but you could be using the dictionary from collections, default dict. Okay. And one more thing to quickly note, if you're familiar with try-based questions, you might see something like self.isEnd or something like that to denote the end of a certain element or word or whatever. All of our numbers over here are going to have the same length. And that's one more thing we want to talk about. So when we actually did this questionnaire, everything had a length of 5, right? But what is the length that we're actually going to end up choosing? And the answer to that is going to be 32 because it's given over here, so we know what value we can choose. Okay, so we have that. Okay, so first we have our class defined for the try node, and now what we're going to do is we're going to create a few extra methods inside of this. So this is going to be our final method. Okay, so over here we're going to have an init method, so def underscore init. And what is this method actually going to end us giving? So this method over here is going to create the root node. So the root node I'm talking about is this R node or the master node on the top, which holds all the nodes underneath of it. So when we define our class solution or create an object for it, then in that case, we're going to initialize a root variable. And self.root, and what is it going to be? It's going to end up being a try node. Okay, so now we have the root defined. Okay, and after this, we're going to have two more methods. So one method, and one of the methods is going to be to insert our number. So I'll just call it insert bits. Okay, and what is this number? And what is this method going to take? So we're going to take self, and we're also going to give it a number to insert into our try. So what we do inside of this method is that we're going to give it a certain number. We're going to convert that number into binary, and then we're going to add it to our try. Okay, so now we have that. And finally, we're going to have one more method, and this is going to be for finding the maximum XOR for each of our numbers. So we'll call this find max XOR. It's going to have the arguments of self, and we're going to give it a number over here for which we're going to find the max XOR. Okay, so we have those two methods, and finally, we're going to call those methods over here inside of our find maximum XOR. What I'm going to do is I'm going to start off by calling this method over here. So over here, the first thing we're going to do is we're going to iterate through our numbers. So we can do for num in nums. Okay, so now we're iterating through our numbers. And over here, we're going to insert each of the numbers into our try. So let's do that. So self.insert underscore bits. So we're calling this function over here. And what do we want to insert? We want to insert whatever number we're currently on. So at the ending of this, we should have a try which is fully formed. Okay, and over here, we're going to have a number called max underscore. And this is just going to be whatever number it is, which is the output of the maximum XOR value. And we're going to just start it off with a number or a value of 0. And if there is anything bigger than that, it's going to get replaced with that value. Okay, so for doing this same thing, we're going to do for num in nums, iterate through all of our numbers. And now that we have this, we're going to redefine our max underscore function. And this is going to be the maximum between the old value, so the old max underscore value. And for the first iteration, it's just going to be 0. Or what we're going to do is we're going to call this function over here, find maximum XOR. And what are we going to call it on? We're going to call it on whatever number we're on. So we're going to take the maximum between either of those two. And at the very ending of this, we're just going to end up returning that max underscore variable. And that's it for our find maximum value. And now let's go back and build out these two functions. So we have insert bits over here. So let's go to insert bits. So over here, we're first given a number, an integer value, and we want to convert that into its bits. So I'll just call this bit underscore number. And how do we convert this? So first into binary. So first let's convert it into binary. So binary num. And the problem with doing that is, as you saw earlier, what we actually end up getting is we get 0b and then we get whatever the number is. So I showed you that earlier. And to get rid of those first two values, we're going to iterate through this from the second element all the way to the ending. Okay, so now that we have this, the problem with this is that it's not going to always have the same size. So how do we get everything to have the same size? And in order to do that, Python has this function called zfill or zfill or whatever. Okay, so zfill, and what this is going to do, it's going to fill everything with zeros until it has a length of 32. So now everything we have has a length of 32. So after this, we're going to define our node, and this is going to be the current node that we're starting off with. And we're always going to start off at the root. So right now we're starting off at the root, and now we're going to iterate through each of our bits. So to do that, we can do for bit in bit underscore num. So now we're getting each of the bits, and now that we have the bits, we need to check if it exists as one of the children. So to do that, we can do if bit not in node.children. So if this is true, so that means that the bit does not exist. Then in that case, what's going to happen? We're going to add that bit. So how do we add it? So it's just a dictionary. So we first go to that child node, and we're going to add a new element which has a value of the bit and the key of the bit, and the value for it is going to be an empty try node. Okay, so there we have that. And now we go outside of this if loop, and we're going to change the value of our node. So at the beginning, the node is the root, and now the node is going to be whatever node we currently are on. So the child in this case. So in this case, node is going to be equal to node.children, and we're going to go to wherever it has a value of the bit. And if it was not there, we added it. So we're always going to have that value. Okay, so now that you have this, we're done with our insert bits function. So that's that, and we're not actually going to return anything because we're adding it to self.root. So yeah, we're not returning anything here. Okay, so finally we have one last and final function, which is find max XOR. All right, so let's go through this function. So in the beginning, we're given a num, and we're going to end up defining the same two things. So we have bit underscore num, and we want to define what node we're currently on. So I just copied these two lines. It means the exact same thing. Okay, so now that we have this, we want to store the XOR value that we find. So we're going to have two numbers, right? And what we're going to do is as we're going through those numbers, we're directly going to add to our variable over here called max XOR. So this is going to hold the binary values of our maximum XOR. And what it's going to be is just going to start off with an empty string. Okay, so now what we're going to do is we're going to iterate through each of the bits inside of bit_num. All right, so we have this over here, and over here we're going to check if the bit value is equal to 0. Okay, so if it is equal to 0, then in that case, we're going to define a variable called opposite bit, right? And this is going to this kind of tells us what bit we're looking for. So if the current bit is 0, what are we looking for? We're looking for 1, since we want the maximum value. Else if the bit is equal to 1, then in that case, our opposite bit is going to be 0. Since if we have a 1, we're looking for 0 in order to get the maximum value. So over here, we're going to check if our opposite bit exists inside of the node's children. So if opposite bit in node.children, and remember that the node in the beginning is the root itself. So that's what we're doing over here. So we're checking if that exists. So if it does exist, this is what we're going to do. So what we're going to end up doing is we're directly going to add its value to the max XOR. So if the opposite bit does exist, what is the value going to be that we're going to add? And the answer is obviously the value we're adding is going to be 1, right? Because when we have two opposite values, the XOR of it is going to be 1. So to our string, we're going to add the value of 1. And in other words, that's the same as calling opposite underscore bit. And you could just do 1, same thing. Okay, so after we do this, we need to do one more step, which is we want to change where our current node is. So to do that, we're going to do node is equal to node.children. So we're going to the child, and to the child, in the child, we're specifically going to whatever holds our opposite bit. So opposite underscore bit. So that is going to be the node currently right now. But if this is not the case, what does that mean? That means that the opposite bit does not exist. So our only option is to stick with whatever there is, which is going to be the same as our current bit. That being said, we're just going to add that to our max XOR. So instead of opposite bit, we're just going to add a current bit we are on, since that is the same as saying that we do not have our opposite bit. And now that we have this, we have node equals to node.children, and we're going to go to the bit. Okay, and that should be it for the for loop. So we go through everything, and we get finally we get our max XOR, which is going to be a binary value, right, in bits. And now we want to convert that to an integer. So how do we do that? So we can do int, and then we can do max underscore XOR. Sorry, because that's what holds the value. We're going to do comma 2 since it's base 2. Okay, and after this, so we got the integer, and we want to perform the XOR value with this number over here. Okay, over here we're going to perform it the XOR operation with the number over here, and this is how you define the XOR operation, and then we're just going to do num. Okay, so this is what we're going to end up returning, and that should be the end of it. So if everything is correct, this should get accepted. So let's just submit this. So as you can see, our submission did get accepted. And finally, thanks a lot for watching, guys. So I just want to make it really clear that this solution is probably not the fastest, and there's probably faster ways to do it. But I feel like the point of this video is to more kind of explain how you could go about this using a trie. And I still think like a really fast solution would still use a trie, except that it would just be optimized a lot better than the way I did it. Okay, so hopefully this does help and you did learn something. And thanks a lot for watching, guys. Do let me know what you thought about the video. And don't forget to like and subscribe if the video helped you. Thank you.